Hi guys, so today we're reviewing everything you need to know about circular motion, centripetal force, and gravity. So first let's start off with the circular motion basics. So circular motion occurs when an object moves along a circular path, and the velocity of an object moving in circular motion is tangent. So I drew this out, so imagine this object here is moving counterclockwise. So its velocity would be directed up north because that is tangent to how it's currently moving. But the acceleration of that object, which is moving circular, goes towards the center of the circle. And some examples of circular motion could just be a planet orbiting the sun, a car turning on a curve, or if you tie like a rock or any type of object to a string and then swing it around in a circular path. Now, centripetal acceleration. So the word centripetal means to move towards the center. So centripetal acceleration is directed towards the center of the circle like we said before. And centripetal acceleration is just the acceleration of an object moving in a circular path, and it is caused by constant change in the velocity's direction, not its speed. Remember that velocity isn't just talking about speed, it's also talking about direction. So when an object is moving in a circular path, its direction is constantly changing, and that constant change in direction is what causes centripetal acceleration. And the formula for centripetal acceleration is AC equals velocity squared over radius. Now, centripetal force. This is the force that keeps an object moving in a circular path by pulling it towards the center, and it prevents objects from flying off in like a straight line due to inertia, which is Newton's first law. And an example of this, again, is just like gravity acting on planets in orbit. And there's like two formulas for this. You could use Fc, which is Fc equals mass times velocity squared over radius, or Fc equals mass times centripetal acceleration. And now Newton's law of universal gravitation. So gravity is a force of attraction that exists between any two objects with mass. So the more mass you have, the more force of attraction you're going to have. More mass equals bigger Fg. The more distance you have gives you less force of attraction though. So the more distance makes your Fg smaller. Now, for most of these questions, we're going to be using big G, which is universal gravity constant, which is 6.67 times 10 to the negative 11th. We're not going to be using little g, which is 9.81 meters per second squared, because that's more just for objects that are on Earth's surface. But for these questions in this unit, we're going to be talking about like planets and stuff like that. The formula for this is gravitational force equals universal gravity constant times mass 1 times mass 2 all over radius squared. And now let's do some multiple choice questions. Number 1. An athlete in a hammer throw event swings a 7-kilogram hammer in a horizontal circle at a constant speed of 12 meters per second. The radius of the hammer's path is 2 meters. What is the magnitude of the centripetal acceleration of the hammer? So this question's pretty easy. We just use the centripetal acceleration formula and plug in because they give us all the values. So AC equals V squared over R. It tells us that velocity is 12 meters per second. So AC equals 12 squared over the radius of 2 meters, and that's going to give us, answer choice A, which is 72 meters per second squared. Number 2, two bodies attract each other with a gravitational force of 10 newtons. What will the force of the attraction be if the mass of each body is doubled? So for this question, we need to understand the equation for gravitational force. So let me write this out. I'm going to write it here. Fg equals universal gravity constant times mass 1 times mass 2 over radius squared. Now, in this case, we can ignore big G because we're only doubling mass. Everything else stays the same. So if we double the masses of both bodies, the force will quadruple. And this is because if you double one of the masses, the force will double. But if you double both masses, the force will quadruple, because mass is directly proportional to the force. And let me show an example of this. So the initial force was 10 newtons, right? So let's pretend that mass 1 equals 5 kilograms and mass 2 equals 2 kilograms. And the radius was 1. So 5 times 2 equals 10 over 1 squared. That's just 10 divided by 1, which is 10. Now, let's double both of those masses. So instead of 5, it's going to be 10. Instead of 2, it's going to be 4. and radius stays the same, so over 1 squared. So 10 times 4 equals 40 over 1, which is 40. So now it's 40 newtons, which is why our answer is D. Number 3. If the Earth were twice as massive as it is now, then the gravitational force between it and the sun would be B, twice as great. So this is the same concept for this question. If Earth doubled its mass, it would be twice as great because it's directly proportional. The force would be twice as great. Number 4. When a satellite is a distance r from the center of Earth, the force due to gravity on the satellite is F. What is the force due to gravity on the satellite when its distance from the center of Earth is 3r? So now in this question, we are increasing the radius or the distance. So remember that distance has an inversely proportional relationship to gravitational force. So if distance or radius increases, the force, Fg, will decrease. So automatically we can cross out choices A and C because those are saying that the force either increases or stays the same. Now remember that in the equation, radius is squared. So even though the new distance is 3r, the force isn't going to decrease by 1/3. It's going to decrease by 1/9 because 3 squared equals 9. So that's why our answer is choice D. Number 5. If the distance between two masses were tripled, the gravitational force between them would be A, 1/9 as great. So this is the same exact thing as we just did. Number 6. The gravitational force of attraction between two objects would be increased by what? So we need to increase our gravitational force. So we should know off the bat that we cannot have any type of increase in distance because distance is inversely proportional to gravitational force. So immediately, A, B, and D are all wrong because they all say to double distance. And if you double the distance, the gravitational force is going to decrease, not increase. So our answer is C. Number 7. Centripetal force, Fc, acts on a car going around a curve. If the speed of the car were twice as great, the magnitude of the centripetal force necessary to keep the car moving in the same path would be what? So now we're talking about centripetal force. Specifically, we're talking about the speed. So let's look at the equation. Fc equals mv squared over r. So in this equation, velocity is squared. So when we double our speed, we have to take that square into consideration. So because it's squared, double speed doesn't just mean double the force. It would be quadruple the force because 2 squared equals 4. So our answer would be 4Fc. Number 8. The two centers of two 15-kilogram spheres are separated by 3 meters. The magnitude of the gravitational force between the two spheres is approximately what? So this question is easy. We just use the gravitational force equation and we plug in. So Fg equals big G, which is 6.67 times 10 to the negative 11th, mass 1, 15 kilograms, times mass 2, 15 kilograms as well, and then that's all over radius squared, which is 3 squared. And once we do this math, we're going to get D, 1.67 times 10 to the negative 9th newtons. So number 9. As the distance between two objects increases, the gravitational force of attraction between them will decrease. So remember, as distance increases, gravitational force decreases. It's an inverse relationship. Number 10. Gravitational force F exists between point objects A and B separated by distance r. If the mass of A is doubled and the distance r is tripled, what is the gravitational force between A and B? So let's break this down. So mass A is being doubled while the distance is being tripled. So a doubled mass results in a doubled force. So 2A would equal 2F. But a triple distance, so 3R, would result in the force being decreased by 1/9, or F over 9. So if we combine these two, we're going to get 2F over 9, which is answer choice A. And we're going to skip 11 because this has nothing to do with our topic. Number 12. Which graph represents the relationship between the magnitude of the gravitational force, Fg, between two masses and the distance r between the centers of the mass? So we have r and Fg. So remember, when distance increases, gravitational force decreases. And it's also going to be an exponential decrease because in the equation for Fg, radius is squared. So our answer is going to be choice A. 13. Two objects of fixed mass are moved apart so that they are separated by 3 times their original distance. Compared to the original gravitational force between them, the new gravitational force is 1/9 as great. So this is the same exact concept. The radius is squared, so they are separated by 3 times. So instead of 1/3, it's going to be 1/9. Number 14. The Hubble telescope's orbit is 5.6 times 10 to the 5th meters above Earth's surface. The telescope has a mass of 1.1 times 10 to the 4th kilograms. Earth exerts a gravitational force of 9.1 times 10 to the 4th newtons on the telescope. The magnitude of Earth's gravitational field strength at this location is what? So this question is a bit hard, and you're definitely going to need your reference table for this one. So the vocabulary they're using is a bit tricky, but if you look at the last page of your reference table, gravitational field strength is just little g, and gravitational force is just big G. So in this case, little g is not 9.81 meters per second squared because we're not on Earth. The location is 5.6 times 10 to the 5th meters above Earth's surface. Now, if we want to find the value of gravitational field strength, we need to use the equation G equals Fg over mass, which is on the reference table. So G equals 9.1 times 10 to the 4th newtons over mass, which is 1.1 times 10 to the 4th kilograms. And once we solve this out, we're going to get C, which is 8.3 newtons over kilograms. 15. A satellite weighs 200 newtons on the surface of Earth. What is its weight at a distance of 1 Earth radius above the surface of Earth? So first off, we're increasing the distance from Earth, so our gravitational force has to decrease. So C and D are automatically wrong. Now let's draw this out. So this is the Earth, and this is our satellite, right? So if we start from the center of Earth, 1 Earth radius only gets us to the surface. We need 2 radiuses in order to get to the satellite. So now that we have in mind, let's look at the Fg equation. So Fg equals big G times mass 1 times mass 2 over r squared. Now, our distance here is 2 Earth radiuses, so r equals 2. But since r is squared, it's actually 4. Now, since it's in the denominator, it's going to be 1/4. So if we want to find the new weight with this new distance, we're just going to multiply the original 200 newtons by our ratio of 1/4. So 1/4 times 200 newtons is equal to 50 newtons, which is why our answer is A. Number 16. As the mass of a body increases, its gravitational force of attraction increases as well. Remember, mass and gravitational force have a directly proportional relationship. 17. Which graph best represents the relationship between mass, m, of a satellite launched from Earth and satellite's distance, r, away from Earth? So the answer here is going to be B, because mass has no relation to distance. Mass and distance both affect gravitational force, but an increase in distance is not going to do anything to mass. 18. Which graph represents the relationship between the magnitude of the gravitational force exerted by Earth on a spacecraft and the distance between the center of the spacecraft and the center of Earth? So this is the same exact thing. More distance is going to be less force. So that's D, and it's exponential because of the square. 19. If the mass of one of two particles is doubled and the distance between them is doubled, the force of attraction between the two particles will what? So when our mass doubles, mass, it's going to be 2F. When our mass doubles, our force is going to double. And when our distance is doubled, our force is going to be quartered. It's going to decrease by 1/4. So ultimately, the change in distance is going to outweigh the change in mass. So even though mass is increasing the force by 2F, the distance is going to be decreasing it by 1/4. And that's going to outweigh it. So we're going to have an overall decrease. 20. On the surface of planet X, a body with a mass of 10 kilograms weighs 40 newtons. The magnitude of the acceleration due to gravity on the surface of planet X is what? So we know that to find weight, we use Fg equals mg. And we have mass and weight, so we can just plug that in to find gravity. So 40 newtons, so our Fg is 40. That equals our mass of 10 kilograms, and we need to solve for g. So g is going to equal 4. So our answer is B. 21. A stone on the end of a string is whirled clockwise at constant speed in a horizontal circle as shown in the diagram below. Which pair of arrows best represents the directions of the stone's velocity, v, and acceleration, a, at the position shown? So, remember that centripetal acceleration is always pointing towards the center. So it's going to be like this. It's pointing towards the center. And the velocity is always tangent to however the object's moving. So this object here is moving clockwise. So the stone will be going down like this. So our answer is going to be D. 22. An astronaut weighs 600 newtons at the Earth's surface. If he doubles his distance from the Earth's center, his weight will be what? So this is the same as question 15, but here the distance is doubling, right? And remember, since distance is increasing, the force will decrease. So because the distance is doubling, and in the equation for Fg, radius is squared, not only will his weight decrease by 1/2, it's actually going to decrease by 1/4 because 2 squared is 4. And we just multiply 600 newtons by 1/4. So 1/4 times 600, and that's going to give us 150. Okay, now I'm skipping this whole page because it's just the same concepts that we've been over. So 26. A 1,200 kilogram car traveling at a constant speed of 9 meters per second turns at an intersection. The car follows a horizontal circular path with a radius of 25 meters to point P. The magnitude of the centripetal force acting on the car as it travels around the circular path is approximately what? So centripetal force is super easy. In this question, it gives us all the values, so we just plug it into the equation. So Fc equals mv squared over r. So Fc, it tells us that the mass is 1,200. The velocity is 9 meters per second squared all over the radius of 25 meters. And we're going to get a value of C, 3.9 times 10 to the third newtons. Now 27. The diagram shows the top view of a 65 kilogram student at point A on an amusement park ride. The ride spins the student in a horizontal circle of radius 2.5 meters at a constant speed of 8.6 meters per second. The floor is lowered and the student remains against the wall without falling to the floor. Which vector best represents the direction of the centripetal acceleration of the student at point A? So remember, centripetal acceleration points towards the center. So if the student is here, then the acceleration would be going towards the center, just like this. So our answer is going to be D. 28. A 1 times 10 to the third kilogram car travels at a constant speed of 20 meters per second around a horizontal circular track. The diameter of the track is 1 times 10 to the second meters. The magnitude of the car's centripetal acceleration is what? So this is, again, really easy. We just plug the numbers into the centripetal acceleration formula, but they give us the diameter here, and we need radius. So we just divide this by 2 to get the radius. So AC equals v squared over r. So AC equals 20 meters per second squared over the radius. So 1 times 10 to the second meters, divide by 2, that's just 50. And we're going to get an answer of D, 8 meters per second squared. So now this is going to be our final multiple choice question. So 29. What is the magnitude of the gravitational force between an electron and a proton separated by a distance of 1 times 10 to the negative 10 meter? So for this question, we need to find gravitational force. So we're just going to use the FG equation, and we need the masses of an electron and a proton, which is on our reference table. So FG equals big G, so 6.67 times 10 to the negative 11th, times the mass of an electron, which is 9.11 times 10 to the negative 31, times the mass of a proton, which is 1.67 times 10 to the negative 27, all over the distance or the radius they gave us, which is 1 times 10 to the negative 10th. And once we do this math, we're going to get C, 1 times 10 to the negative 47th newtons. So now we're going to do some short response. Number 1. A 925 kilogram car rounds an unbanked curve at a speed of 25 meters per second. If the radius of the curve is 72 meters, what is the minimum coefficient of friction between the car and the road required so that the car does not skid? So this problem might seem a little confusing because it talks about coefficient of friction and skidding, but let me explain. The first thing we're going to do here is solve for centripetal force because remember, the centripetal force equation is Fc equals mv squared over r. And in this question, it gives us all those values. So let's just solve for that first. So Fc equals 925 kilograms times 25 meters per second squared over a radius of 72 meters. And this is going to give us 8,029.5 newtons. So now that we have Fc, we have to ask ourselves, how can we find coefficient of friction with this? So since we need coefficient of friction, at some point we need force of friction because that is the only equation which contains mu, aka coefficient of friction. So let's look at the wording of the problem. In the problem, it tells us that the coefficient of friction is what's keeping the car from skidding. It's making sure that the car won't fly off in a different direction while it's driving the curve. So remember that centripetal force is the force that keeps an object moving in a circular path. So in this case, that frictional force between the tires and the road is also what's keeping it moving in a circular path. So in this scenario, force of friction is equal to centripetal force. So since we know that FF equals FC, we can just solve for coefficient of friction using the FF equation, which is FF equals mu Fn. So now we just have to solve for Fn and then plug in for FF. So Fn is just going to be mg, so 925 kilograms times 9.81 meters per second squared. We can do this because it's just on Earth like normal. And this is going to get us 9,074.25 newtons. So now FF equals FC. So FF is equal to 8,029.5 newtons. Plug everything back in. FF equals mu Fn. 8,029.5 newtons equals mu times 9,074.25 newtons. So we're going to get a value of 0.88 for coefficient of friction. Number 2, a small plane makes a complete circle with a radius of 3,282 meters in 2 minutes. What is the centripetal acceleration of that plane? So the centripetal acceleration equation is AC equals v squared over r. So it gives us radius in this equation, in this problem, but it doesn't give us velocity. So we have to find velocity by ourselves. It tells us that the plane makes a circle with a radius of 3,282 meters in 2 seconds. So to find velocity, we need to do v equals d over t. So to find the distance that it traveled, we have to find the circumference of that circle. So circumference, if you guys don't remember that equation, it's 2 pi r. So we just plug in, so 2 pi times the radius 3,282. That's going to give us a distance of 20,621.4 meters. And since the plane made that circle in 2 minutes, we have to convert 2 minutes into 120 seconds. and now we can solve it out. So the velocity is going to be 20,621.4 meters over 120 seconds, which is 171.85 meters per second. So now we have velocity and radius, we could just solve it out. So AC equals v squared over r, so 0.85 meters per second squared over 3,282 meters, and that is going to give us a value of 9 meters per second squared. Number 3. A 2.7 times 10 to the third kilogram satellite orbits the Earth at a distance of 1.8 times 10 to the seventh meters from the Earth's center at a speed of 4.7 times 10 to the third meters per second. What force does the Earth exert on the satellite? So this question is pretty easy. We just need to use the equation for centripetal force because it says that the satellite is orbiting the Earth. So Fc equals mv squared over r. And we just plug it in. So Fc equals the mass. It tells us 2.7 times 10 to the third kilograms times the velocity. It tells us 4.7 times 10 to the third meters per second squared over a radius of 1.8 times 10 to the seventh meters. And we're going to get a value of 3,313.5 newtons. Number 4. Kirk, 80 kilograms, is sent to a planet that has a radius of 2.61 times 10 to the 7th meters, and he finds that he weighs 1,250 newtons there. What is the mass of that planet? So remember that weight changes while mass stays the same. So your weight will change depending on your location because gravity is different on different planets. So on this planet, Kirk's weight, or his gravitational force, is 1,250 newtons. And in the problem, it also tells us that Kirk's mass is 80 kilograms and the radius of the planet is 2.61 times 10 to the 7th meters. So we have all these values except for the second mass, or the mass of the planet. So we can just solve for the mass of the planet by using the Fg equation. So Fg equals big G times mass 1 times mass 2 over r squared, and we just plug in. So we know the Fg, it's 1,250 newtons. Big G is 6.67 times 10 to the negative 11th times mass 1, that's going to be Kirk's weight, 80 kilograms. Mass 2 is the mass of the planet, which we're trying to find. And the radius is 2.61 times 10 to the 7th meters squared. And once we solve this out, we're going to get a mass 2 of 1.6 times 10 to the 26th kilograms. Number 5. Determine the force the moon exerts on an object with a mass of 80 kilograms if that object is on Earth. So once again, this question is talking about the force exerted on an object, so that is going to be Fg. So Fg equals big G times mass 1 times mass 2 over r squared. So we have the mass of the object, which is 80 kilograms, but we need the mass of the moon, which is exerting the force on the object, and we need the distance between the Earth and the moon because the object is on Earth. So all these values are on the first page of our reference table, so we just look for those and then we can solve. So Fg equals big G, 6.67 times 10 to the negative 11th times mass 1, that's going to be the mass of our object, 80 kilograms, times mass 2, that's going to be the mass of the moon, which is 7.35 times 10 to the 22nd kilograms. And that's going to be all over the radius, or the distance between the Earth and the moon, which is 3.84 times 10 to the 8th squared. Now, once we solve this out, we're going to get an Fg of 0.0027 newtons.